I'm going to be reviewing how to graph a rational function, and the problem I'm doing comes from 2.4. I just pulled number 48 out of the book. This function is f of x equals 3x squared over x squared plus x minus 6. So to graph this, the first thing you want to do is find x and y intercepts. To find an x-intercept, you change y to 0. So that's going to give me 0 equals 3x squared over x squared plus x minus 6. If I multiply both sides by this denominator, these will cancel out, and I get 0 times this stuff is just 0. 0 equals 3x squared. It's actually a shortcut. This is always going to happen. X-intercepts will happen where the numerator equals 0, because when you multiply both sides by the denominator, it's always going to go away. So 0 equals 3x squared. Solve this, you get 0 equals x. That means our x-intercept happens at 0. Since the x-intercept happens at 0, I know the y-intercept is also going to be 0, but just in case it's different, here's what the math would look like. To find the y-intercept, you change x to 0. So plug in zeros for all of those x's, which gives me 0 divided by negative 6, which is 0. So the y-intercept is at 0. All right, next thing they're going to ask about is asymptotes. Asymptotes happen, vertical asymptotes happen, where the denominator equals 0. We can't divide by 0, so those asymptotes are places where this graph is undefined. So it's going to be undefined where the denominator equals 0. To find that, I'm just going to factor the denominator. Factors of negative 6 that add up to positive 1 are x plus 3 and x minus 2. So if x equaled negative 3, that would make this piece equal 0. Or if x equals positive 2, that would make that piece equal 0. So these two places are where we're going to have vertical asymptotes. They're also going to ask about horizontal asymptotes. Horizontal asymptotes can actually get pretty complicated, but in our textbook, we are going to only look at two situations. First situation we're going to look at is where the degree of the numerator is exactly equal to the degree of the denominator. If the two degrees are exactly equal, then the horizontal asymptote will happen at the ratio of the leading coefficients. So 3 is our leading coefficient here, 1 is our leading coefficient here. Ratio means divide. 3 divided by 1 is 3. So we are going to have a horizontal asymptote. At y equals 3. If these two degrees had not been the same, like let's just say if it had been 3x over x squared plus x minus 6. If this degree down here is greater than the degree that's up here, then the horizontal asymptote is always at y equals 0. The other cases that we don't cover in class is if this degree is greater than this degree. Don't worry about that. Make sure you know that if the degrees are exactly equal, the horizontal asymptote happens at the ratio of the leading coefficients. If this degree, if the numerator is less than the degree of the denominator, the horizontal asymptote will be at y equals 0. Alright, so using all this information, we can start to sketch what this graph is going to look like. So I know that my x and my y-intercept happens to be the same here at x and y equals 0. I have vertical asymptotes at x equals negative 3 and x equals 2. So asymptotes are usually dotted lines, and here they are at negative 3 and positive 2. My horizontal asymptote in this problem is going to be up here at y equals 3. And we almost have enough information to figure out what this graph is going to look like, just a rough sketch of this graph. Since we almost have enough, but not quite, the rest of it is picking a few points and plotting them. So I picked, a minute ago, I picked -4, since -4 would be on the other side of this asymptote. I also picked -1, since it would be between this asymptote and this point. I picked +1, since it would be between this point and this asymptote. And I picked +3, because it would be on the outside of this asymptote. So I plugged them into my function. I did this with just let my calculator do all the work. I plugged in -4 into this function. So -4 squared times 3 and -4 in here. Actually, I did it with the factored version. It was a little bit easier. So I plugged -4 in for all of these x's, and my calculator spit out that if I plug in -4, I output 8. Which means back on my graph, I've got a point of -4, 8. Which would be right about there. I plugged in -1, like I said. If I plug in -1 in for all of these x's, I got out -0.5. So go back 1 and down 1/2. I next plugged in +1 for all of those x's, which gave me -0.75. So +1 down 3/4. And the last point I plugged in was +3. When I plugged in +3 into my function, I got out 4.5. So over 3 and up 4.5. So now that I've got some points on here, I know what this graph is going to look like. Let's look right here. These points have got to connect. And I know that the graph isn't going to come back up because it would have to cross the x-axis, and I would know about it. There would be another x-intercept that we would have found clear over here when we were finding x-intercepts. So I know it doesn't cross the x-axis again. And rational functions always either shoot up by a vertical asymptote or shoot down. Since it can't shoot up without crossing the x-axis, it must shoot down. Same reasoning over here. Can't shoot up, or it would have to cross this asymptote, or sorry, it would have to cross this x-axis. I know it doesn't, or we would have found an x-intercept. And it's got to shoot up by an asymptote or shoot down, so it's going to shoot down. Up here at this point, we're going to have this kind of shape. It's going to shoot up near that asymptote, and this horizontal asymptote, this is what horizontal asymptotes do, is they make the graph look like this. Horizontal asymptote is a description of end behavior, so this is going to start looking more and more and more like this line as we get out to infinity. Same situation over here. We've got this point that's up by this asymptote. It's going to come down and start looking more and more like a line over here. If you don't trust yourself with this, pick a few more points to plot, and you're going to get that your graph roughly looks like that.